First of all, a very good morning to you. My name is Muzmuli Vishal, and I'm going to teach you the benzene, the hexagon null structure, cyclic structure. Uh, so on the left, you are seeing a hexagon, that we have seen since childhood. It's like a six-sided structure, but there is another add-on that there are the bonds, the three bonds that have shown. uh, what is significance of these bonds, what is significance of this hexagonal structure, uh, why we present any hydrocarbon with this structure, what are significance. uh, these are some of the objectives I am going to clarify for you in this session. So let's start with the benzene and aromatic character. That's the point of this presentation. First of all, I will introduce you what are the fats and what are the aliphatic compounds, aromatic, and what it were denoting in the past time in chemistry, and what are they denoting today. First, it was like the aromatic compounds were like that, the compounds that are giving the fragrance, odor, and but today the concept is different. uh, the aromatic compounds have certain properties, uh, characteristics that it should possess to say it the aromatic compound. And there are the second class is aliphatic. Uh, the aliphatic, it is same because of the chain the it forms. There are no cyclic structure. The carbon with their catenation property form long chains, and because these long chains are generally seen in fatty acids, uh, triglycerides. Because of that, they were in past also called as fatty acids. So what are aromatic compounds today? uh, and why I am telling the aromatic compounds? Because the benzene that we are going to study is one of the first aromatic compounds we got in 1868. August Kekule from University of Bonn gave the benzene, one of the cyclic hydrocarbon, and because of his dream or his mental picture of benzene, we got this structure, and now we are standing in the position that this is the most studied aromatic compound. So why are we studying it? Because aromaticity is possessed by benzene. So what are aromatic compounds? Aromatic compounds basically are cyclic compounds with uh, some specific amount of pi electrons forming pi clouds above them, below, above and below their planar structure. There are conjugated bonds. These conjugated bonds are continuously resonating, and this is helping in the extraordinary, or we can say a different stability than what we see in uh, aliphatic hydrocarbons. So what the aromatic compounds like benzene, that resemble benzene in chemical behavior, because benzene is the first one to be studied. We will like compare any cyclic structure with benzene to study it. If it shows similar behavior with that of benzene, we will say that it is aromatic. So which behavior or which characteristic will be studied? We will study it as the structural properties. Structural properties? Because chemistry is dependent on structure. Every property that we are going to study of every compound, any compound in chemistry, any element, then its property is actually due to the structure. Structure is what everything is controlling. The structure will make it reactive, less reactive, uh, specific reactions, stability, distability, everything is with the structure, whether at elemental level or at complex formation. So then what are aliphatic hydrocarbons? As I have told you, aliphatic hydrocarbons are hydrocarbons with long carbon chains. These long carbon chains are actually mm, uh, seen in fats, and so these are also we are called as fatty acids. Aromatic hydrocarbons are characterized by tendency to undergo ionic substitutions, that is electrophilic aromatic substitution, that is only seen in the aromatic compounds. The so this this is structure of benzene, given by Friedrich Kekulé, August Kekulé, in 1868. He is from University of Bonn, and there is actually an interesting story behind it. So I will tell it in short, that he was sitting resting at his fireplace, and he thought that uh, in his mind he was thinking about the aromatic compounds that he was studying. Then he made a mental picture of snakes, 2 to 3 snakes, uh, taking their tails in the mouth, and they were mockingly like circling, moving in circle. And then he studied some days on this idea, and actually this was true. Like we can say, his mental picture actually resembled the benzene, and that's how we got the mm, structure of benzene. Then there were many properties, chemical properties that were shown by benzene, that actually made us to accept this structure. And these properties, we can say, are first the benzene's molecular formula. When we do mass spectroscopic studies of benzene, then we will get like proportionality of carbon and hydrogen. There we will get the mass of carbon of 6 carbons and 6 hydrogens, and from this we get the molecular formula 66H6. Here is that small interesting story. You can pause and read. And from this molecular formula C6H6, we then we are like, before Kikul proposed the structure of all the scientists were like, what structure we can suggest. Then these were some of the structures that we are actually suggest. The first one, the Kikul structure of benzene that we are having uh, to date. Then because of isomer number and other properties of or other properties considered, the scientists gave, the chemist gave the structure of like, they were one of the chemists. Then the third one is having a 5 carbon cycle. Then one of the carbon is bonded to another CH2. Then fourth structure is given by two triple bonds, and then the fifth structure was given with two double bonds and one triple bond in the center. But we can here only tell that the two structure, based on the our studies, that the last two structures are not that supporting the C6H6. And if this was the structure, then we have didn't would have not studied it to this extent. Then the second property, that benzene resembled the structure was that benzene undergoes monosubstitution. Monosubstitution product is like if we do bromination or chlorination, halogenation, any halogenation reaction with benzene, only one structure was given. That's because of the significance that characteristic, we can say that all the hydrogens that are in benzene, all the carbons and every electron in the benzene, a pi electron cloud from pi electron cloud is actually, we can say, from the pi electron cloud is actually equivalent. It's not like any hydrogen has a different properties, different stability, and another hydrogen is having different stability. Everyone is equivalent, and because of this, any of the hydrogen could get lost during substitution reactions. And because of this, if we use the reagents that will give us monosubstitution. The monosubstitution will give only one product. We cannot say that the monosubstituted product has substituent on first carbon, second carbon, fourth carbon, fifth carbon. Yeah, if a benzene has monosubstitution, then all the hydrogen, because all the hydrogens are equivalent, there we will get only one monosubstitution product. We can show it like here are examples like chlorobenzene, nitrobenzene, like that. And then the another third point that will make us accept the benzene structure given by Kekule's structure was that we will get three isomers, structural isomers of a disubstituted benzene product. When we will do a disubstitution of any benzene, like dichlorobenzene, trichlorobenzene, sorry, dichlorobenzene, uh, dibromobenzene, dinitrobenzene, chloronitrobenzene, any product with two substitutions, then we will get three isomers only. Uh, because of this one, I will go back to that structures. Here you can see that only Kekule's, if Kekule structure we can we if we take the Kekule structure in our studies, we can say that all the hydrogens are actually equivalent in only Kekule structure. The hydrogens in Dewar structure are also different because they are all connected or bonded to the carbon, which are having double bonds in, and some are not having double bonds. Some are sp2 hybridized, some are sp3 hybridized. In third structure, the story is actually very different, and fourth and fifth, uh, there are hydrogens that are equivalent, but then the third property of disubstitution will kick out the fifth and fourth structures. So the important point in disubstitution is that we get different isomers, structural isomers, like 1,2 dibromobenzene. If we do the bromination or halogenation, bromination type halogenation of benzene, then we will get dichlorobenzene, dibromobenzenes like 1,2 dibromobenzene, 1,3 dibromobenzene, and 1,4 dibromobenzene. We have to understand that we can also show 1,2 dibromo 1,3 and 1,4 with the help of ortho meta para OMP, and we can also resemble these numbers 1 2 1 3 1 4 with OMP respectively. Then the third property that we are going to study that made us accept the benzene Kekule's structure as benzene is the benzene undergoes substitution. benzene will not go free radical substitution. It will not undergo any type of addition reaction. The only reason behind this is that we we will say that if it undergoes free radical substitution or addition reaction, the it will in free radical it will have to form a free radical, yeah, where it will have to lose one electron, and in case of with an atom, and in case of addition reaction, it will all have to accept some electrons from the substituent that is going to come in, but without losing any electrons, and this will disturb what we call the Huckel rule of aromaticity, uh, based on which we explain the aromaticity. And because aromaticity is not because aromaticity is dependent on this property of uh, Hakel rule of aromaticity, which aromatic compounds has to follow to have that extraordinary stability. So to avoid this, uh, mm, benzene will always undergo substitution. So it will lose atom, and in the place of that atom, that's obviously hydrogen, another atom will come in, and the aromatic character that benzene is having will be preserved, uh, and it will preserve the stability that is benzene is having, which is because of the pi electron cloud above and below the carbon plane. So the actual structure of benzene is like, there is a plane of carbons. Carbon plane is there. Then all the carbons are with sp2 hybridization, which makes them to be in the plane. Then the pi orbitals are above and below this plane. So it's like uh, carbons, and then sandwich between the pi electrons above and below it, and these pi electrons are actually uh, they are having hub bonds, forming hub bonds with every two pair of electron every two pi electrons that are near them, and this makes the extraordinary stability of benzene. And to preserve this, the benzene will undergo substitution, uh, so that this cloud will always will be preserved, and this will give the stability that we want. So benzene undergoes a substitution rather than addition. So some here are some of the reactions that we generally see in non aromatic hydrocarbons, mm, and that we see in benzene. So in like it will not react with KMnO4, it will not undergo uh, any type of uh, different addition type of reactions like bromine addition, then or the reaction of halogenation reaction at lower energy states, that will make it impossible to give such energy state that it will undergo substitution. And then it will not undergo any type of hydrogenation, it will not undergo any type of hydrogenation or any type of halogenation, that is with the help of any hydrogen halides. Then another point, these are some of the na- reactions of benzene that are substitution electrophilic substitution reaction, in which this nitration, sulfonation, halogenation, they will have to first form a electrophile. So why electrophile? Is that I told you in the structure that there is a planar benzene, there are electron cloud above it, electron cloud below it, and because these electrons are readily available for reaction, and because of this, and this is forming a nucleophile. Then electrophiles will be formed. These electrophiles only can react with this uh, circular cyclic structure of benzene, that will make the substituent, and this electrophile will be substituent, and it will undergo electrophilic aromatic substitution. So here are some of the examples, like nitrating mixture of nitric acid plus sulfuric acid. Then we can also undergo sulfonation with the help of S2SO4 with SO3, so that it can form uh, benzosulfonic acid, and in first one nitrobenzene. Halogenation reactions in which um, in which it, the reagent of a metal which can undergo different which can have different what can we say, a metal which can have different uh, sta- compounds with halogen, like FBr3, AlCl3, uh, A or FeCl3, so that it can undergo different products. It can be in also in FeCl2, FeCl3, so that halogenation will take place. That's the property of uh, the metals. So these metals are actually reagents in halogenation reaction, and this with halogen will help in halogenation of the benzene. Then the Friedel-Crafts alkylation and Friedel-Crafts acylation, in which the AlCl3 that we have seen in halogenation, will in alkylation we will take an alkyl halide plus the reagent AlCl3, FeCl3, and this will help us to get an alkylated benzene, or we can say alkyl benzene. And then Friedel Craft alkylation acylation, sorry, Freedom Crafts acylation. In this we will react acyl chloride or acyl halide, we can say any hydrocarbon we transformed into acyl halide will be reacted with benzene to give a ketone product. So the next point will be is heat of hydrogenation and heat of combustion of benzene. So if we take any structure like cyclohexane, like it has only one double bond between two carbons in the whole six carbons. Then at that time we do hydrogenation at with platinum, palladium metals in with the in presence of hydrogen gas. Then we can say that the heat of hydrogenation will be like about uh, 20 to 28.6 kilocalories. But in when we see this in the other alkanes, no sorry alkenes alkynes, in alkenes a double bond will be hydrogenated at with the energy exchange of about 25 to 30 kilocalories. But uh, then if we go on adding like mathematically only, then we will get energy of about 54 5 point something energy in kilocalorie energy for hexane diene, cyclohexane. Then in cyclohexane trine we should get energy exchange of about 86 kilocalories. But actually it is not seen in benzene. And here we also again get the reason why we don't get this energy change is because of the uh, extraordinary that stability that we have always been seeing in benzene. So Here is a chart that is been shown. So at cyclohexatriene, if we go on mathematically doing this, then cyclohexatriene should have like energy of 85 86 kilocalories after hydrogenation. Yeah, but this is not seen. There is only exchange of 49 kilocalories, and this change that we have got two values of 49 and 86 85. There is like a change of energy, potential energy change of 36 kilocalories, and this energy is called as a resonance energy, because we got this energy due to it the resonance. It is called as this change due to resonance, it is called as resonance energy or resonance stabilizing energy. Then the another point that we can see in benzene is that uh, the carbons the bonds length in carbons, what we see in general is that 1.54 Armstrong is the length of 1.5354 is the Armstrong is the length of single bond in between two carbons. Between the double bond of, in alkanes is like 1.50 or 1.49 Armstrong. In case of like 1,3-butadiene, like dienes with um, two double bonds in the compound. That's also in conjugation, like double bond, then single bond, and then again double bond. In this, we see that the bond length is about all the bond lengths are about like 1.40 or something, 1.48, and what we get in double bond in alkanes is 1.34. So we will like without going rationally, we will if go simply, then we will say that uh, we will say that the bond lengths in benzene should be of two types. We should get the bond length that we have seen in 1,3-butadiene also. Uh, that's are three bonds, and three bonds of single bond length, that 1.53 or something. But this is not the case. We don't get this. We don't get these results, and the results are different, that all the bond lengths in carbon are actually having same bond length, that's 1.39 Armstrong. So why we get this is again because of the half bonds that are formed between two carbons. uh, the I'm seeing the half bonds because the pi electrons are actually having interaction with both the pi electrons nearby it, and because of which it will form like interaction of about energy of a half bond, and because of only this, the more stable the bond will become. Always one and half bond will be more stable than a single bond, and because of this, though it is a pi bond, it will reduce the length between two carbon atoms, and this will cause more stability, again the extraordinary stability that we say about the benzene. So these are some points that we considered, that chemists considered in accepting the structure of benzene from Kekul's structure. Then what about resonance structure of benzene? Like we said that there is interaction between two neighboring pi electrons of a unique pi electron of a carbon. So for this simplicity, if we start learning carbon in first when we study the chemistry, then we should have a simple structure, and for this we have accepted the structure of Kekule, and there are two resonating structure, and these are the first structure that we are denoted on the screen, and the second structure that denoted. This can simply be given in the 1 and 2 that we can again see in right hand side on the screen. So the first one is and second one, these both are we should have in mind that both the structures are having being they are being in this form. The benzene in this is in this form, or the electron cloud is in this position, in the half time in the first form, in half time in second form. So and this is cycle is always going. It will go from 1 to 2 to 1, 1 to 2 to 1, and this will always go endlessly. So this we have to consider in first place when we start to learn the aromatic compounds, and we start to learn about the benzene. But the actual structure is different when we go on studying the we go on studying the in higher classes. We should always have